Well, welcome to another Common Core Algebra 2 lesson. In tonight's topic, we're going to look at factoring, specifically the sum and difference of two perfect, check this out, cubes. So we've kind of graduated from perfect squares, and we're going to step up our game, and we're going to talk about factoring perfect cubes. This is a topic that's historically been a pre-calculus topic here in New York State, and so this is our first crack at it here in this class. Before we dive in, though, I'm going to talk about a specific career called actuarial science, and this is a really hot field these days. And there is a lot of money associated with this particular field, and we've had a few graduates over the last few years land some really nice jobs and be financially well off. But basically what it boils down to is you are in charge of measuring risk, whether you work for an insurance company or a finance company, or in fact it's branching out into other fields. The new big thing in sports now is analytics, and basically what you're doing is you're measuring risk and trying to make educated moves based off of that. So before we get into the perfect cubes, let's review our perfect squares. First of all, our list of perfect squares that we've gotten really comfortable with is 1, and then 4, 9, 16, 25, 36, 49, 64, etc., etc. But it wasn't just limited to integers. We could also say, well, x squared is a perfect square, x to the 4th, x to the 6th, x to the 8th, so on and so forth. Those were all algebraic expressions that happen to be perfect squares. Now, when we were factoring the difference of two perfect squares, you know, we might have started off with something simple like x squared minus 4, and we saw how that factors into x plus 2 times x minus 2. And we were able to verify that, and all we had to do was multiply, use the distributive property here, and we could verify that it does indeed equal x squared minus 4. However, do you ever wonder why we never talked about the sum of two perfect squares? And basically, let's say we had x squared plus 4. Believe it or not, that does not equal x plus 2 times x plus 2. And in fact, it's impossible to factor the sum of two perfect squares. And if you having trouble buying into that, we could certainly, what we could do is we could substitute a specific number for x. Like we could say, well, let's let x equal 6 maybe. And so we've got 6 squared plus 4, and we're saying that doesn't equal 6 plus 2 times the quantity 6 plus 2. And so 36 plus 4 is 40, and that doesn't equal 8 times 8, which is 64. So just basically know this, it's impossible to factor the sum of two perfect squares. Okay, now we're going to tap the brakes here and introduce you to what perfect cubes are. And I think once you see the process, you're going to be able to really run with it and make it your own. So when we say 1 cubed, we're really saying 1 times 1 times 1, which equals 1. So 1's our first perfect cube, not a very exciting one though. 2 cubed says 2 times 2 times 2. It's all about repeated multiplication, isn't it? And that turns out to be an 8. So 8's also considered a perfect cube. Let's see, 3 to the 3rd power, 3 times 3 times 3. And of course, once the numbers start to get big enough, we're definitely going to lean on the calculator. And don't be afraid to use that calculator as a tool here. 4 times 4 times 4 turns out to be 64. So 64 is interesting. He's not only considered to be a perfect square, but he's also considered to be a perfect cube, which makes him a pretty special number. 5 cubed, 5 times 5 times 5 turns out to be 125. 6 cubed is 6 times 6 times 6 equals 216. So there's a nice fun one to memorize. Let's do one more here. 7 cubed, 7 times 7 times 7, that's going to turn out to be 343. And obviously the pattern continues, and if we wanted to do 8 cubed, 9 cubed, so on, you guys could easily pick that up yourself and run with it. So here's our list of perfect cubes, starting with 1, 8, 27, 64, 125, 216, and 343. Those are all considered perfect cubes. Now what we're going to do later on, if they want to know what is the cubed root of 343, well, that's just going to equal 7, because we know that 7 times 7 times 7 equals 343. Now, just like perfect squares, our discussion on perfect cubes isn't limited to just integers. In fact, we're going to look at some algebraic expressions that contain variables that are also considered perfect cubes. And specifically, in this discussion here, our algebraic expressions is going to refer to monomials only. And that'll be nice. That's going to keep it nice and simple. So for instance, if I said, x raised to the 3rd power, well, that means x times x times x, which, well, it's just x cubed, so x cubed is considered a perfect cube. But what if I stepped it up and I said I want to take x squared and raise him to the third power? X squared times x squared times x squared. Well, that turns out to be x to the 6th, and if you want to break that down even further, it's x times x times x times x times x times x, which is where the x to the 6th comes from. What if I said I want to take x cubed and raise him to the third? X cubed times x cubed times x cubed equals x to the 9th. And I bet you can see where the next one's going to go. It's all about identifying patterns. And if I add these 4's together, I'm going to get x to the 12th. And so you can see the list starting to develop. We're going to cheat a little bit. The next one would be x to the 15th. The next one would be x to the 18th. And then x to the 21st, so on and so on. And what you're noticing is all the exponents are multiples of 3. So these are all considered to be perfect cubes. And just to reiterate that, if they ask me later tonight for the cubed root of, let's say, x to the 15th, well, I would say that's just simply x to the 5th, because I know that x to the 5th times x to the 5th times x to the 5th equals x to the 15th. Now, you want the insider secret? If you take this exponent and divide it by 3, you'll always get the correct cubed root there, x to the 5th. Now, that only works with exponents. Don't try that with normal integers. Now that we've got you good and warmed up with what a perfect cube is, let's look at some of the binomials that we might be factoring tonight, and we're going to start off with sums. Interestingly enough, we convinced you in the beginning of the video that it's impossible to factor the sum of two perfect squares, but it's very possible to factor the sum of two perfect cubes. And that's just going to make our job a little bit harder tonight. It's going to give us an extra formula to worry about, but it's nothing we can't handle. So tonight, something we might look at is how to factor x cubed plus 8, because both the x cubed and the 8 are considered perfect cubes. Or we might factor something like 27 plus y to the 3rd, or it might be something like x to the 6th plus 64, or it might be something like, it might even get crazy and it might say, oh goodness, they could say 27x to the 12th plus 8y to the 9th, and every term in there is considered a perfect cube. Conversely, basically, examples of difference of two perfect squares just means we're replacing the plus signs with minus signs. So now it could be x cubed minus 8, or it could be 27 minus y cubed, etc., etc. Like we said, we're just replacing the plus signs with minus signs, but they're all perfect cubes still. Well, you've probably had your highlighter sitting next to you in your notebook the whole night so far and maybe haven't had a chance to use it. Well, I tell you what, this is the slide to use it on. These are going to be the two rules that we really take with us tonight as we do each example. But here we go. If we still have a binomial that says a cubed plus b cubed, here's the rule. It's going to be the product of the quantity a plus b times the quantity a, whoops, why did I write an x? I don't know. Let's make that an a. A squared minus ab plus b squared. Okay? Wow, that's a mouthful. But once we practice it a few times, I think it's going to roll right off the tongue. Now, if I do the difference of two perfect cubes, such as a cubed minus b cubed, all right, now it's going to be the product of the quantity a minus b times the quantity a squared plus ab plus b squared. Now you'll notice they're almost the same. The only thing that's going to change are these signs. Like sometimes it's a plus sign, sometimes it's a minus sign, or sometimes it's a minus, sometimes it's plus. But look at that last one. This last sign's always going to be a plus sign no matter what. Now you're wondering, how am I ever going to remember that? Well, let me show you a really sweet rule. SOAP, it stands for same, all right, opposite, and then always positive. Same, opposite, and then always positive. And I'll tell you what that means here really quick, if I can squeeze in positive. Okay, what it means when we say same is this first sign is always going to be the same. Okay, so if you start with a plus sign, that first sign's always a plus sign. Or if you start with a minus, then you start with a minus here. So it's always going to be the same sign. Now the next sign is going to be the opposite of the one you just did. So again, if you had a plus here, the opposite is going to be a minus. Or if you had a minus here, the opposite is going to be a plus. And then like we said, the last one's always positive no matter what. So it's going to be same, opposite, always positive. Same, opposite, always positive. And that, ladies and gentlemen, is how we're going to remember our signs. Alright, we're going to dive into our first live example here, and what we have here is it's going to be the difference of two perfect cubes, and I'm saying the word difference because of the minus sign here. Now the first thing I'm going to do, especially for my first example, is I'm just going to rewrite the rule that I want to use, and it's the rule that says a cubed minus b cubed equals a minus b times a squared, why did I write an x again? Oh my goodness, plus ab plus b squared. Okay, so that's the rule that I'm going to work off of. And basically, if you want to make a note off to the side here, the letter A is equivalent to an x because that's what's getting cubed here in the first term. And the letter B is equal to a 3 because that's what's getting cubed in the second term. So if you want, you can rewrite this as x cubed minus 3 cubed. And you can clearly see who your A and your B values are. So my factored form is going to be x minus 3 times the quantity x squared plus 3x. Oops, I gotta fight to squeeze this last one in there. Plus 9. Okay, and basically what you'll notice here is every time I saw the letter A, I substituted an x, and every time I saw the letter B, I substituted a 3. Okay, and remember, it's same, opposite, always positive, and we got the right signs. Now what we're going to try to do is we're going to try to verify it this one time. In other words, we're going to try to check our answer. Now as this says, we can feel free to choose either the distributive property or the tabular method. And you know what I'm going to do? I'm going to go with the tabular method right now. And I feel like we're pretty darn comfortable with that. In fact, I've been really impressed with both of our methods. It's as good as I've ever seen. So I'm going to go x squared plus 3x plus 9 there, and I'll do x minus 3 on this side. And what I'm going to do is I'm just going to multiply, and that's going to give me 3x squared plus 9x, and then I've got negative 3x squared here, I've got negative 9x there, and I've got a negative 27 there. And what you'll notice happening here is when I add, these two terms cancel each other out. When I add again, these two terms cancel out. So the final sum is just x cubed minus 27, which is the original binomial I started with. So check, or you can put a little happy face there to say we just verified that the product is indeed the original problem. So a couple of things here. First thing you want to say to yourself is we're working with the sum of two perfect cubes, not the difference. And I'm saying sum just because of the plus sign here. Now, two things I want to do first. First of all, I'm just going to refresh my memory as to what the formula is that I'm working with. And so we know that a cubed plus b cubed is really always going to be a plus b times a squared minus ab plus b squared. Okay, so that's the formula that we've got to know, and like we said, with a little more practice, it's going to roll right off the tongue. Now the next thing I like to do is I like to ask myself, well, what's getting cubed to create these terms? And in order, so I'm asking myself, what raised to the third power equals y to the 6th? And hopefully you feel comfortable saying y squared. And then I could also say, well, what raised to the third power equals 8? And again, hopefully you feel comfortable saying a 2. And so I'm thinking to myself, my a is equal to y squared, and my b value is equal to a 2, and now I can go ahead and make these substitutions. For instance, every time I see an a, I'm substituting a y squared, and every time I see a b, I'm substituting a 2 right here, and right here. So let's go ahead and let the magical substitutions begin. Alright, so we've got a plus b, y squared plus 2 times the quantity. Let's see, if I take a y squared and then square that, I get y to the 4th minus 2y squared plus 2 squared, which is 4. And that is my final factored answer. And again, we could verify that one as well, either with a tabular or distributive property, to end up just checking to see that the product equals y to the 6th plus 8. Well, we got a little harder problem here for you. And the first thing you're going to notice is that although 8 to the ninth might be a perfect cube, 2 certainly isn't a perfect cube. Now remember, 8's a perfect cube, but 2 is not a perfect cube. And you can also scan that list we made earlier, and you'll notice that we don't see 432 on that list either. So what gives? What's going on here if neither one of these are perfect cubes? Well, make sure this pops out in your notebook, okay? We're going to always check for a GCF first. Always check for a GCF. Alright, so ask yourself, what's the GCF of these two terms? Well, I can at least factor out a 2. So if I take out a 2, that's going to leave me with 8 to the ninth minus 216. And here's the good news, alright? 8 to the ninth is a perfect cube, 216 is a perfect cube. What we've got here is a difference of two perfect cubes. Now, again, what I like to write is I like to ask myself, well, what's getting cubed to make a to the ninth? And I said a to the third was getting cubed. And then again, what's getting cubed here? It's a 6. So when we think about our formula, the a cubed is your a value and the 6 is your b value, and now it's just a matter of substituting into our formula. Let me see if I can slide over a little bit here. Alright, so remember your SOAP principle. Same, opposite, always positive. So I need a cubed minus 6, because I need the same sign. Now, I need a cubed squared, or a cubed raised to the second power, which is a to the 6. Alright, now I need the opposite sign. It's a times b, so I've got 6a cubed, and then plus 36. I got to make some more room here. There we go. And so that is our factored form. A lot more challenging than the last one. Maybe if I'm worried about anything, it's going to be this term right here. If I did that too fast, I'm thinking a cubed raised to the second power, and again we could multiply the 3 and the 2 to make this 6 right here. Okay, by far the most challenging one of the night, and I cannot imagine them getting any harder than this one. And I promise you, if you can get your way through this one, there's nothing they can throw at us on a test, quiz, or the final exam that's going to even compare to this one. So here we go. The first thing, like we said on the last slide, we've got a problem because 192 is not a perfect cube, x to the 8th is not a perfect cube, 375 is not a perfect cube. This problem really looks like a disaster. But remember, we're going to look for a GCF. Okay, and here's the deal. We got to wrestle with this one, and I want to encourage you not to give up and to just keep trying things on your calculator. So what I've got my calculator in my hand right now, and I'm going to just start dividing 192 by random numbers. 192 divided by 2, which works, but the problem is 375 is not divisible by 2. So then I'll try the next number. I divided them both by 3, and I said winner, winner, chicken dinner. Both 192 and 375 are divisible by 3. Now, what else do these two terms have in common? I see some x's in both of these terms, and it looks like they both have at least an x squared, so I'm going to factor out an x squared as well. Okay, so 192 divided by 3 gives me 64, and then I could say, well, x to the 8th divided by the x squared gives me x to the 6th. Plus 375 divided by 3 is 125, which is a perfect cube, and then the x squared is gone because I factored it out, and all I'm left with is y cubed. Alright, now we can let the fun begin. Let's see. What did I have to cube to make 64x to the 6? And I'm going to say it's 8x squared. And what did I cube to make 125y cubed? I'm going to say it was 5y. So what I'm thinking is 8x squared is my a value, 5y is my b value, and now it's just time to plug in. And I guess instead of working from left to right or horizontally, I'm going to work just straight down here. And I'm going to carry down the 3x squared. And let's see, the first term is going to be a plus b. So I got 8x squared plus 5y. Then I need a squared, so oh my goodness, 8x squared raised to the second power would be 64x to the 4th, minus a times b, which is going to be 40x squared y. And then the last term is going to be b squared, which in this case is 25y squared. I got to fit my parenthesis in there. And this is my final answer. And you know what? I haven't checked that last slide, but I feel like I left off my GCF on my answer on the last slide. So if I did that, I think the GCF was a 2 on that last problem. If you could attach that 2 to my final answer, I'd appreciate that. So that's what we're looking at, ladies and gentlemen. We're going to continue to work on these rules, and I tell you, we finished with some really hard ones. So if these last 2 problems bothered you, don't lose any sleep over it. 90% of our problems tomorrow are going to be much easier than that.